Um, First of all, I would like to thank you all for signing up for our webinar and for taking your time and for being here with us today. Let me first just go over a little bit of logistics. So we're going to run this webinar for about 30 to 40 minutes. You all are muted. And to ask questions, please use the panel on your right side, which like the GoToWebinar panel, where you can find question. There is a bar that says questions and chat. So feel free to send your questions to the chat bar. And what we're going to do is we're going to pick up all these questions at the end of the presentation and answer all of them between Tim and myself. In case for some reason you start losing me, or I don't know, something goes wrong with the sound or with the video, just also please send a note to the chat bar and we will try to fix it. So let us begin by introducing ourselves. So my name is Vlad Perezin, and I'm a Senior Vice President of Exapinos. And I'm a geophysicist by background, but now drilling optimization is my biggest passion. And I will let Tim Robinson to introduce himself.
Thanks very much, Vlad. So I'm also a physicist by background. I did the PhD in plasma physics, but professionally I've been working in the applied machine learning and data science space for the last several years.
Fantastic. So we will handle the webinar between the two of us. If there are any very like tough questions at the end, we promise you, and if we cannot answer them, we promise you to come back to you with answers. But again, please feel free to use the chat to send your questions as we go through our webinar. So what we're going to talk about today is we're going to talk about StackPipe. And before we do this, let me just say a few words about us as a company. I mean, what we do is we are an IT company, and we are focused on developing machine learning applications that are focused on very specific tasks to address drilling performance. Basically, what we're working on machine learning applications that can either predict or detect and eventually prevent the drilling hazards. And today we're going to talk mostly about the drilling hazards that are related to the pipe obstruction. Any type of pipe obstruction is that you can have during your operations, but also there are other machine learning applications that we're working on that we will be covering in other webinars, such as ROP optimization real time or predictive maintenance, things like motor failure, tool failure predictions, well control management, kicks, losses. All these things actually can be handled by machine learning very well. But we're going to cover those in other presentations, in other webinars, and today we're going to focus only on StackPipe issues. So with a StackPipe, you probably know that actually this is the reason why we start with StackPipe, is because it is a major cause of non-productive time, right? So it's it is also the most costly incident that you can have in your operations. So this is where most of your costs related to non-productive time goes to, and it results mainly to things like differential sticking, which is like your well bore stability, your mud cakes, things like this. but also things like mechanical sticking, and which are more dynamic frictions related to the movement of the pipes, hole cleaning issues, so jammed pipe, that result in jammed pipe, and all these incidents that occur either during different type of operations, right? Trimming, reaming, drilling, any type of standard operations. These things can happen, and the idea here is that if you can have a machine that can detect early symptoms of this type of incidents, right, and can alert you and warn you about potential risks of these incidents to happen, then it provides amazing value, because if you have enough time to react on those warnings and alerts, then you actually have a chance to avoid them and prevent them from happening. Also, we believe that machine learning can do a much better job than a human to detect those very, very early symptoms and deviations and very subtle events that humans either don't have time to do this, or it's hard to spot those things and it's hard to absorb them, or it's hard to interpret them. What are they related to? So that's what we're going to focus about today, is stack pipe and what machine learning can do for you. So what can actually do for you? Let's talk about this a little bit. Well, it actually can do a lot of things. It can improve your situational awareness. Obviously, as you drill, you know better what's happening if you have some kind of a system that tells you what is going on right now, and if there are any risks that you need to be worried about. So detecting those early systems, but also identifying its nature. So like not only, hey, there is some kind of a risk, and then it's kind of meaningless because you really don't know what it is related to. But if you do, and you know that it's related to, let's say, a hole cleaning issue, or to wellbore stability, or to some tight spots, in your areas, then you know much better what to do. So all this, of course, can help to reduce the non-productive time and ensure that that real-time monitoring centers actually do a lot more than just monitoring. That they actually can react on this and can prevent and avoid these drilling hazards. So now we're talking about machine learning. So what is really a machine learning? So we're going to cover just a little bit about what is a machine learning and how that works. I don't know, Tim, can you tell us more about what is actually machine learning?
Yeah, definitely. I might launch into that, but it just looks like the slides that you're presenting are not changing. It looks to me like it's still on the title slide. So
is it?
I'll just start covering your question while maybe perhaps a quick look at that. So yeah, machine learning at its core is a set of computational methods that lets us build models which can perform certain tasks, and we do that based on some kind of historical data typically. Now, the nice thing about machine learning compared to other approaches with modeling is that you don't have to explicitly tell these models how to make their decisions. So that's the real power. They can kind of learn from past experience, from data, and then perform these tasks accordingly. So classic tasks in the machine learning space might be regression, which is predicting a number of some sort, or classification, where you're predicting some kind of label or outcome, perhaps. Now, machine learning is actually all around you in your day-to-day life, and you may have already realized this, but some of you perhaps not. And great examples of that are, for example, if you unlock your phone using your camera in your face, that's facial recognition, that's computer vision. There's probably a convolutional neural network sitting somewhere in the background which is recognizing your face. Other things might be if you have a virtual assistant like Alexa or something, there's again a lot of applied machine learning going on in the background there. There's trigger word recognition, there's processing your your speech into text transcription and then understanding what to do with that with a knowledge graph, perhaps. After that, they've got to then turn the text from their response back into speech. There's all kinds of machine learning going on in the background there. Another good example is if you use streaming services like Netflix or Spotify, whatever it might be, or social media, like TikTok or Instagram, Facebook, LinkedIn. These are all using content serving algorithms in the background. So recommendation systems are super important and commonly exposed to us in our everyday life. Finally, another classic application is anomaly detection. So if you have ever been exposed to a banking system, they tend to do a lot of fraud detection in the background. Not very well, to be honest, in my opinion. But nonetheless, that's another very classic use of machine learning.
Okay. Can you see my slides now?
Still looks like title slide to me. Perhaps one of the audience, if you can just post a message in the chat saying if you're seeing a title page or something else.
What do you guys see? If you could write in the chat box what you see. Do you see just the title slide or? Okay, I don't see. So it's still title slide for you, Tim?
Yeah.
Let me start.
If it's just me, don't worry about it. I mean, other people can, if they can see it, that's fine.
Let me start. I'll stop sharing and start it again. Let's see if that's going to happen. That's going to help. Can you see it?
Yeah, it's the right one now.
Okay.
Yeah, so everyone can see my nice examples there.
If I change it, can you see it?
Yep, all good.
Okay, perfect. All right, sounds good. So let's just continue with this. And the next thing we wanted to, so we just wanted to tell you a little bit about where is oil and gas industry in all this. I mean, internet, in other industries, we know that machine learning and artificial intelligence is used there. But where do we stand in oil and gas? Basically, just to give you a little bit of context, machine learning can do three things. It can do descriptive analytics. Basically, it will tell you what just happened, right? So it will look at what happened and will try to analyze it, right? And to understand what just happened. Then, if we know what happened, then maybe we can predict it. So that's the next level of analytics and of the machine learning, is actually to be able to predict things. Once you know what it is, then you can try to predict it. And then the third level is, okay, if you can predict it, then maybe you can prevent it, and you can actually prescribe certain actions that would allow the user to prevent this from happening. It's called prescriptive analytics. If we look at a little bit about at the history of the machine learning, we know that it's more or less started to develop in 90s, but it's very researchy, right? So actually only in 2000s when it started to actually grow significantly with all the CPU power and everything, being much more affordable. So I would say mid 2000s is when it started to grow. But the thing is that, and then as everything grows, data sizes, computer power, of course, it's going to become better and better, and it will progress from machine learning to a true artificial intelligence, not what somebody called artificial intelligence now, which is not. I mean, but would actually go to a true AI, and that's going to take some time. And where do we sit with an oil and gas? Well, we're actually somewhere here. Okay, so we actually in predictive kind of analytics step, and we are probably about 10 years behind of how machine learning is used in other industries, in medical industry or internet or space or any other industries. So so we are behind, and well, for some very good reasons. One reason being the oil and gas industry is extremely conservative, and you probably all know that very well. But also the other reason is because our data is quite bad. I mean, it's actually very, very bad data to, in terms of machine learning analytics. Why? Because it comes from different type of tools, it comes from different methodologies, it always has different formats, and it's changing all the time, and it's not consistent. So to handle this type of data is actually not easy by something like machine learning because it's not standardized. The underlying physics are also not consistent, right? Because we're drilling in different environments, in different lithologies, with different technologies. So everything keeps changing, from well to well, right? So it's never exactly the same. And then the classic kind of machine learning approach that look at mainly statistics, they don't work. And believe me, there's been a lot of companies that try to take whatever worked in Google or in some other areas, right? And or Microsoft, analytics, and try to just, plug in oil and gas data and hope for the best. Well, that failed miserably. So these are all the bad news. Now, the good news is that what we found out is that some very special machine learning technologies that are informed about basic engineering principles can actually still be very, very efficient for oil and gas when it is applied for very narrow tasks, specific tasks, not big things, So you need to go for like very small tasks, and and this is how the digital transformation may happen, is if you break it down into small tasks and have different type of machine learning kind of doing these different tasks for you. And then also the good news is that it looks like the drilling operation that is happening in different places by different companies actually have a lot of things in common, and displays very common patterns. So no matter where you drill and what equipment you use, there's some elements of drilling behavior that is the same and repeatable, and actually can be analyzed by the machine learning. All right, so let's go now into a little bit more about how to make this machine learning work. Tim, what do you think? What is needed to get the machine learning kind of efficient at drilling optimizations?
Yeah, that's a great question. So I like to think about building solutions in this space from a few different perspectives, and there are a few principles I use normally when building a product in this area. So first thing here is written on the slide, right? The idea is these tools is they should support engineers and not add to their workloads. You shouldn't have to work for the software. Software should work for you. So that's the kind of the number one thing, and that ties very well into that third point on the bullet there. So low effort. But some of this has been touched on by Vlad already. We like to target our tools towards specific, in the context of hazard prevention, risk indicators, which are linked to something physical. So for example, in the context of stuck pipe, what is a stuck pipe? It's where you can't move a pipe, right? So if you have difficulty rotating something, or difficulty lifting something, or restricted flow that comes from a packing off of the wellbore, then all of these things can be identified by looking at the right piece of data that streams off of the rig. So that's what we like to do. We like to think about the physics that actually relates to what being stuck means, or what the underlying sticking mechanisms are, and then we attack all of those directly in our solution design. So another thing that's really key, which most people, in my experience, tend to underestimate, is having something that works consistently across operations. So many oil companies are operating globally. So ideally, if you have a tool that needs to be able to work in every operation that a company could possibly have, it's not much point having something that works in Argentina but works nowhere else in the world. That wouldn't be a good way of doing things. So what we like to do is we use data that is reliably available all the time, We'll touch more on the nature of this in the next following few slides. But another thing that consistency involves is being able to get consistent performance across operations. So the first part is being able to use something consistently. The second is to get consistently good results. And one of the things which people are very aware of in the industry is that humans can be imperfect at spotting risks. So, there may be good reasons for that. There might be, in the 11th or 12th hour of a 12-hour shift, could be tired, there could be something distracting them, it could be something else. The nice thing about using a software solution, though, is these sorts of human factors are not so consequential for you anymore. All right, so I touched on the element of low effort already, but the key thing there is when we want to have a solution, we design it such that it's easy to set up, configure, and then you can use it in this plug and play model straight out of the box. Move to the next one, please. All right, cool. So let's expand a little bit more on what I meant earlier about using this kind of targeted approach. So we have our modules or agents which look at very specific characteristics in physics which relate to these known risk factors. I mentioned some of these already. So resistance to rotation, being able, difficulty lifting something. These can manifest, as you would expect, in maybe the hook load or the torque or those kinds of measurements that we take from the surface. So by having various agents targeting all these different risk factors at the same time, you can not only identify the risks, but by looking at the combination of these risks found, you have quite interpretable insights about a stuck pipe risk. For example, let's say you see problems with pressure, you see problems with rotation, and problems with translational motion that's lifting up and down. Yeah, you probably have something which is packing off the pipe, right? There's a flow restriction and a physical restriction. So based on looking at all those three different factors, which are reliably flagged by the software, you can think, okay, this is probably a pack off situation. And then the mitigating actions that you would need in different types of stuck pipe situations can then be correctly chosen because you have a good view over what the interpretation behind a risk is. Another key thing when this is more on the modeling side of things, when setting up a machine learning pipeline, is you need to have good data that is quite representative of the problems that you are looking to recognize. So, for example, if you are always operating in one specific type of well, let's say, and then you want to have a model that works really well in something quite different. So let's say HPHT wells, high pressure, high temperature, are more towards the extreme end of things. Something like that, if you have none of that represented in your initial data sets, then it's unlikely that you'll get very, very good performance in these sorts of things. So curation of data is really, really important when designing any solution. Just lastly, I'll give one example around how we like to target specific aspects of physics and then use engineering expertise from our colleagues from the drilling industry in terms of how we would formulate these kinds of approaches. So if we think about differential sticking, it's a very classic risk mechanism for resulting in stuck pipes. So one of the problems with this is that this is where I should say that you have a pressure differential between the formation fluid and the wellbore fluids. And so when the drill string is static, so it's not been moved or up and down or rotated, then you can get an elevated risk of this. So what is the sign of that when you try and move again? It's the force required to either rotate or to lift something up or lower it down. So things like the breakover hook loads and the breakover torques, if you look at this piece of information specifically, can tell you a lot and really help you identify those risks. If you were just to look at a time series of hook load or torque and use a classification model, for example, based on those time series, and it label some data and try and catch it, that's much more difficult to do, much more difficult to extract that information. So we use these engineering principles in order to break that barrier. Next step, please. Okay, cool. So I mentioned before that we are looking at very specific risk contributors when it comes to stuck pipes. So the three main ones that we look at in order to get good results with stuck pipe detection and prevention are differential sticking, mechanical sticking, and hole cleaning. So I kind of talked about a few of these already, and differential sticking we just discussed, it's to do with static friction. And then hole cleaning, again, as I mentioned before, where debris is not being cleaned correctly out of the wellbore, and this can build up and cause a restricted flow, pressure restrictions, fluid friction, and oscillations in ECD. That's the equivalent circulation density, I should say. So the other thing on this slide here we have is mechanical sticking, and that's where you'll in dynamic conditions you'll observe difficulties in moving the pipe, as whether that be vertically or could be horizontally, but let's say in a translational plane or in a rotational plane. So in order to look at all of these different things, this can be done by considering surface data. This is really reliably available. Some examples of that data is given in this orange box here. Okay, let's move to the next one, please. So consistency is key. I just mentioned reliability of data being available, and surface data is really good for that, because pretty much every rig will record all of these pieces of information, normally with good enough sampling frequency to do something useful with it, and then it can support a piece of software like this. If you use other forms of data, you can get good results often, let's say downhole tools. However, these are not always reliably available. Different operations might use different downhole tools. So you add a lot of restrictions in some ways of how applicable a tool is if it's too dependent on downhole data. So that's something to bear in mind whenever thinking about a software solution in this area. So leaning into this theme of consistency, I mentioned before that a computer doesn't suffer from the same kind of attention deficits that a human might do. So you can, with the software, spot these risks consistently across operations, whether your monitoring specialists are tired perhaps, or whatever it might be, their training level. A common complaint that we've heard in the industry in the last few years or so is that there's a lot of talented staff are leaving the industry and not being adequately replaced. So it may be the case that on a particular operation that you have, that the staff operating it are not all as skilled as each other. You might have some who are better than others. With software, you can level that playing field. So someone who's not super experienced can, when augmented by software, provide the same level of monitoring capability as someone who has had much experience in the industry. And another thing that helps with consistency is that when you have warnings which are based on some kind of sound physics, they're easy to verify, and it's much easier to make a decision based on that when you have a good understanding of why something might happen. Next one, please. So we discussed it a little bit at the beginning. Low effort is really key in our opinion when working with any kind of software solution. So what does this mean? You want minimal effort to set something up. One of the criticisms that physical models have had which are the industry standard, had in the past, is that you need to make a lot of decisions for setting configuration values and settings of these ahead of doing a simulation run. These models also often make quite unrealistic assumptions. So on top of the effort you have to go to configure them, some of these assumptions are quite problematic and not always very well communicated. An example of that is, let's say you're trying to model downhole equivalent circulation density, the ECD. So normally a fluid model will be used for that. And most of these models, which are commonly used in the industry, are making the assumption that you have a perfectly cylindrical wellbore and no drill string rotation. Now, anyone who knows what rotary drilling is will realize that that's not a very good assumption to make. So using a machine learning solution, you can often avoid making these explicit assumptions and make use of information like the rotation that is otherwise being neglected by these physical models. So a few other things really help to make these tools low effort to use. One of them is automatically detecting the rig states that are happening at any one time, so you know what kind of risk factors to look out for. If you have no flow when you're tripping, then looking for problems to do with that flow is not very relevant. So that's a very simple example of rig state detection, but it can go to more complex things. One of them we'll touch on later, for example, is detecting downlinking, which is done via the mud pulse telemetry system. With our tools, at least, we have the capability of doing these things automatically. So what does this mean? If we can do that automatically, you have minimum setup efforts. That minimizes the amount of human interaction needed to get something going. And then the consistency that comes from the software tools means that it minimizes the amount of interaction during an operation as well. So the last thing that is really important, in my opinion, to make sure these things are low effort and then transferable across operations is for the models, the machine learning models that sit under the software to be very well generalized. So what that means is if you've trained a model on a particular set of data, let's say wells 1 to 10, then it should also work really well on unseen wells 11 to 20. So that's what we do when we're thinking about a model training. We build models and validate them on completely different data. So by having this kind of split in your data sets, it means that you can have quite a good degree of confidence that your tools will work when exposed to an entirely new operation. And you'll see how thinking about this helps us with performing well on new operations when we go through some blind test results in our case study section a little bit later in the webinar. All right, so what does generalized models mean? It means you don't have to use any offset well data for pre-training for an operation. You can get going straight away. All right, and one thing that a lot of people will often ask about is, okay, you can detect these kinds of hazards, but does this software generate loads and loads of false alarms which are going to annoy the engineers? One thing to bear in mind is that every single false alarm has a cost, even if it's a small cost relative to a catastrophic stuck pipe event, which means you have to sidetrack or plug and abandon or whatever it is. But those, if you have a lot of false alarms, that small cost can quickly become problematic. So at Exobenus, we're really focused on ensuring that we have really low false alarm rates. And traditionally, with machine learning tools, which are at its core, this is a classification problem we're talking about, warning of a risk or not warning of a risk. People tend to compromise on the sensitivity of a tool, its recall, its ability to identify all of the positive meaning of risk cases. And that's normally a trade-off with how many of the positive flags, the warnings that you raise, are actually valid ones. So this is the kind of classic paradigm that people are working with in the classification space. However, if you inject a bit of external knowledge into this domain expertise, then you can break this paradigm by looking at the root causes, or the underlying causes, I should say, of why you might see a false warning. So there's a couple of examples of this I'd like to share within this session. That's the first one is downlinking. I mentioned that earlier. On the picture at the bottom here, we have a pressure trace, and this shows you what downlinking looks like. So what they're doing here is communicating with downhole equipment by sending trains of pulses through the drilling fluid. That's mud pulse telemetry. Now, what that means is that you have quite large pressure disturbances. If you look relative to the relatively stable pressures towards the end, these downlinks are very, very large pressure changes. So if you have tools which are monitoring pressure, this can interfere with them a little bit and be a source of false warnings. However, you don't need to compromise on this. These things can be detected by other tools. So if you have a risk detection tool based on the pressure, but also something that can detect downlinking, then you can drastically cut down the number of false alarms that you might get from something like this, while not having to compromise on the sensitivity versus false alarm rates of a tool. Another kind of classic area where you see sources of false alarms can be these transitions between different operations, or rig states that a team is working with. So I mentioned earlier that automatic rig state detection is really useful. If you have this, then these transition states no longer become a problem. So through that, we've had really good experience with dropping down the number of these false warnings, and while still maintaining the ability to catch all of the risk factors as they develop.
Okay. All right. Thanks, Tim. And when we talk about when we talk about the machine learning and what can it do for you, I know we're talking about stack pipe right now, but the question that we always are asked is, hey, my stack pipe, it's not such a big issue for me, but I have some other problems that cause a lot of NPT. Can machine learning help with that? And there is a whole big array of those little things that are super annoying that machine learning can actually help, because these things are predictable. They do have symptoms that machine learning can detect at a very early stage. And I'm talking about things like predictive maintenance, motor failure, tool failure, lithology classification, safeguarding, like vibrations or bit balling detection. Also talking about ROP optimization opportunities, right? So all of that can be done by machine learning. So it can cover the full spectrum from risk detection all the way to optimization of your drilling performance. Right now, we're covering some at Exabenos, but our objective is to have machine learning applications, or how we call them, agents, machine learning agents, to actually, to cover all those issues and have each separate agent to attack, and answer and all these different challenges. Now, what kind of value it brings? So before we jump into case studies, I just wanted to show you this one, which is a really, really amazing case study. This is from our big client in East Asia, in Southeast Asia, and they have been with us since the beginning. So they actually have been using the software for about 3 years now, and they used it on over 200 wells right now, and they were very thorough at collecting statistics about actually was it helpful or not. So and what we got, and this is published by them, so you don't have to believe us. But what it says is that basically, in average, they used to have about 20 stack pipe incidents per 100 wells, and then in 2017, they started to use some type of analytics to actually try to understand what's happening, to try to predict what's happening. So they used some analytical tool. It was painful. They had like it was a lot of work from their side, and so. But what it did, it actually helped them to reduce significantly, this amount to only like 4.5 stack pipe incidents per 100 wells. Since 2020, they're using our software, no pain, and they now got it down to 2.6. So it's almost tenfold reduction of stack pipe incidents. Imagine how much money they save. All right, so let me show you how it actually works. We have a little video for you here. Hope you can see it. So we have like a short video, and I'm going to pause it for a second. Just to show you what you're looking at. So this is just like a standard tracks that you visualize in any WITSML viewer that you use. We can actually integrate with different viewers, WITSML viewers. So here on top, you can see that there is just some standard drilling parameters, and we only use surface drilling data. So standard drilling parameters, and then the next 3 tracks is our output. Is basically where we plot our alarms and warnings and our data. So this one is differential sticking, as you can see, mechanical and hole cleaning issues. So in this particular case, and this is a real case study. So in this particular case, I'm going to just start from the beginning. You can see that everything kind of going well in terms of mechanical and hole cleaning. But in the differential sticking track, this yellow things are the warnings, and the red are the alarms. So you see those warnings are being raised, and then they're followed by an alarm. So warning is like low to medium risk, and alarm is medium to high risk, right? So I'm going to just play this video for you. So it just continued for about an hour, showing these warnings and alarms. on differential sticking. So clearly showing there are some issues with static frictions, with static friction as you drill, and so you can see that it actually intensifies. The alarms are now more, the warnings are now more alarms, so they kind of, the frequency and the severity is intensifying, and then they got stuck here. And they were stuck for like 78 hours, I think, in this particular case. So, so if you count those like early warnings, like from here to the point where they got stuck, this is about 2.5 hours. So we could actually predict, we can predict those incidents with a sufficient enough time, to make appropriate actions and mitigate these risks. So this is how it works. We wanted to make sure that it's a very clear indication. It's easy, right? It's like a traffic light system, right? So green, yellow, red, and so it's easy to view, to visualize. It's easy to understand. It's easy to interpret, and it's easy to act on them. A lot of people ask us, what is actually a communication protocol? How does this work? Okay, so I do see an alarm. What do I do? Okay, and again, this is very individual because every company has their own operational procedures and their own setup. But typically, what we do is we read the WITSML data from the WITSML store, and we use it, we analyze it. So, by the way, I forgot to mention that our software name is Spotter, right? So because we spot things, right? So Spotter would analyze all this information, and will actually provide this information either to a real-time operations center. Some companies have this set up, especially like bigger companies, they have their real-time operations center, or to rig site where you have drilling supervisors, you have mod loggers, you have other like engineers that are watching the operations, right? So the people that involved in monitoring, they get alerted, and there's certain communication protocol between them, right? And so then they make a decision on how to prevent those things from happening. Okay, so now let's jump into case studies. So we have prepared several case studies for you from very different regions and different type of wells, different lithologies, different operations. So this particular one is from US. It's unconventional, from US land. It's client that actually first wanted to try it with us, right? So we do a lot of trials with our clients, and we can do these trials for you guys as well. So basically what they did is they said, well, we want to test it first, and to do this, we're going to give you free wells, just only wells, just only time logs, and we're going to cut them before an incident, and so that you cannot like back engineer, like reverse engineer the alarms, which of course we never do, but people are worried that it can happen, right? So they gave us those free wells, and you can see like on this one well here, on the mechanical sticking, you can see again the warnings, kind of showing up, turning into alarms, and also intensifying towards the end of the interval. We saw the same situation on the second well, and on the third well, actually it was all clean, with no warnings, no alarms, nothing. So we came back to them. We said, look, looks like you may have got some problems here on this particular well, and then on the next well, and they said, well, actually, exactly, because what happened is that we got a stack pipe incident right like about an hour after this interval, right? And on the third well, they didn't have any stuck pipe incident, and they just tried to trick us. So that basically means that we got 100% accurate all their incidents, and we had no prior knowledge about offset wells or their well specifics or any type of particular things about these wells. The only thing we got were just time wells. Okay, so we didn't know anything about these wells. This is just to show you how important it is to have an application which is a true plug and play, where you don't need to do any pre-modeling, you don't need to do any pre-training of your models or anything, or any type of time-consuming operations beforehand. So this is completely out of the box and ready to go. It's super important because it can be scaled to any number of wells. You don't want to spend a lot of time, and then make sure that everything works on one particular well, and then spend another, again, all this time again to make sure that now it works on the second one. You just want this to work anytime, on any well, anywhere you drill. That's another case study, very similar to the previous one, also a post-analysis, like a blind test. Actually, this one was not a blind test, I'm sorry. This one was a look-back analysis, with a company in Middle East. So they had a well, they were drilling, they actually were tripping out. Then the rig crew noticed something happening with obstruction. So they thought they're going to mitigate this by circulating. So they started to circulate like crazy, circulate. Then they continued to trip out, and then they got stuck. Now, then we ran our stuff. We ran Spotter on it. So we got this warning here, which detected some problems and some risks. We got another one here. Then they were circulating, and then looks like it helped for about 5 stands, but then there was another warning that came up, basically telling that whatever they did was either insufficient or was not appropriate. And what's very, very interesting in this case study is that it actually was not appropriate, because what we detected is not the circulation, it's not the hole cleaning issues. It's an issue with differential sticking with the well bore. So you can circulate as much as you want, it will not help you with this well bore issue, right? Probably reaming would be a better operation to mitigate this particular risk. So this shows how important it is not to only alert, but actually to tell the operator and that what type of risk it is, so that they can take appropriate actions. That's another very good example also. We don't even know where it is from, because we got it from the service company and we have no idea where it is from. But here what we see is that on differential sticking, at the beginning of this interval, we got an alarm that turned into, we got a warning that turned into alarm. At the same time, some hole cleaning alarms and warnings were raised. That was drilling. Then there were some unusual operations that we don't even understand what they were doing here. And then they got obstructed. So it was not a full stuck pipe, but it was an obstruction, some kind of obstruction that they struggled to get the pipe out. And so kind of the same situation is the warnings build up, and this happens about actually very early. So we could see this, more than 6 hours before it happened. So that was quite impressive. This one is an example from a live operation where the tool was used while the well was drilling. And so here on differential sticking for this particular interval, there was a warning, turned into alarm a few stands later. And the rig crew reacted to these warnings and alarms, started to do some reaming. There was also some hole cleaning issues, right? So they started to do some reaming. And then the hole cleaning issues remained. So they probably had to do a bit more of a circulating, or they put like higher mud pressure or something to get. Seems like, from differential sticking, some of the debris has been falling down the well, and that's why this whole cleaning issues got raised here. But in any case, in this well, they didn't get stuck, so it's a happy end. So it's a happy story. So the risk was detected, the crew was alerted, action was taken, and that helped. So basically, it was they didn't get stuck in this particular one. Tim, you want to talk about this case study?
Yes, I mean myself. Yeah, so the thing I like about this one is in this scenario here, we have an example of how you can detect particular risk zones based on the depths within a formation that's being drilled. So what do we have in this scenario? So at the beginning, there's a tripping phase. There's some differential sticking risks being identified in these areas. So as I mentioned earlier on, differential sticking is an interaction between the wellbore and the fluid pressure in there, and a difference between the formation pressure. So formation being the key thing, it's going to be tied in some way at least to a particular type of formation that's being drilled through, so linked to depth. So what do we have after this? Then you see some other warnings, some risks identified. This is a historical data blind test case, I should say. So the rig crew were not actually seeing these. So they later on from the software identified that there were some issues, and then as part of the drilling, they were obviously rotating and then doing some extra circulation in order to keep conditions hunky-dory. So, okay, the risk was partially mitigated by that circulating and the rotation during the drilling, but they still had a couple of odd warnings during that period. And then what we see towards they didn't get stuck in this case, but there was just that remaining risk partially mitigated. However, they were okay through that period, that drilling period. You can see in the sort of central part of this view. Towards the end, they're tripping out again, and they approached that same. Sorry, I should say they were tripping out rather than again, and then they got back to that depth zone that they'd previously encountered with multiple warnings, and then the warnings are back again. So that shows that you can use a tool like this to not only just catch things in real time, but to identify parts of wells where you can have problematic depth zones. Now, the nice thing about that is if you drill any other wells in the future in the same field, then you have a good view based on this type of thing of where you might see similar risks in the future, and you can plan for those ahead of time. All right, this last one is from a live operation in South America, where the real-time operating center for this client actually were using the software and had these warnings available to them. So the key thing that we're trying to understand here is, okay, from the historical blind tests, we can see if the software is able to detect drilling hazards. But the question is, once those are detected, can we actually do something about them on a reasonable timescale, and can processes work accordingly with that? So what we observed in this case is, again, differential sticking risks. Several warnings were raised in the depth zone where you see these yellow bars. Independently of the software, this is not something that was known to us, but which the operations team from the operator told me afterwards, was that this approached a depth zone where they'd had some problems in the past. So nicely consistent with that external validation that we get from that info. So what they did, the operations center there, the monitoring engineers called the rig and they said, you should do some extra flow and some extra rotation in order to get through this zone. So they were able to pass through with some restrictions. You can see here a little bit of difficulty moving, but they passed through. They didn't get stuck. So this is a really nice example of how these warnings were actually used and actions were taken by both the rig and the operations center staff, and a stuck pipe was avoided. And just one thing that I found very interesting when speaking to the same operations specialist from this company was that when they were using the software like this, he had observed that the RTO engineers working with this field were making 50% more interventions when they used the software compared to when they would just be monitoring without software in the same area. So his takeaway from that was that it helps also to improve the alertness of the RTO engineers, It's kind of a nice piece of info that I just wanted to share with you guys on the call.
Okay, very good. So just to summarize about all the studies we've done and all the wells we applied this technology on, and now this is probably, we're talking about a little bit over 300 wells that this has been used on, and across the world. We're talking about different operators in different parts of the world: conventional, unconventional, horizontal, vertical, offshore, onshore, doesn't matter. So over this array of like time period and different wells, we now have some pretty good statistics. So on a lot of our clients, what they do is they do forensic analysis, which is look back analysis, right? So they basically do a post-drill evaluation of the wells using our software to actually see to be able to do different things. One thing is to determine if the incident or the issues that they had at their old wells actually could have been predicted. Because if they could have been predicted, then they could have been prevented, most likely. Then, so that's one thing. They want to see if it could have been predicted with enough time before the incident. Then they wanted to know, what was the main cause of this NPT and the offset wells, right? It also helps to detect the different intervals that has the highest risks, so that when you drill in the same area, you drill new well, you know how to, where are your major kind of areas of highest risks, and what type of approach you need to take in these particular sections. Interestingly enough, when you do look back analysis, you see a lot of non-reported downtime. So something that you thought, something that was missed. Okay, so it's really good to know, and it's not like 2 or 3 hours. We're talking, dozens and sometimes hundreds of hours of non-reported downtime. So obviously all this raises awareness, and you can use all these lessons learned from the previous well to actually prepare a much better, more appropriate drilling plans and procedures for your new wells. It's also very fast to do this type of look-back analysis. It only takes 2-3 days per well to actually do it. So you can, in quite short period of time, take all the wells you drilled before, analyze them, and then use this information to plan much better your next campaign. So that's a forensic type of analysis. Predictive type analysis is something we use in real-time operations. So what we see is that we can actually reliably predict about 96% of all the stock pipe issues and risks. So this is a very strong metric. Very low false positive rate, and the team, already mentioned, how we managed to do this, because this is a very big problem for any machine learning applications. So we managed to keep it very low. So what's very interesting is that out of all the issues and the risks that were detected and that were warned to the to the rig crew and drilling supervisors, only about 64% of these risks that were identified were actually mitigated. So in other cases, they still got some issues. They still either got stuck pipe or some other problems, and that happened because either the indications just went unnoticed, so just nobody paid attention, or the cause was misinterpreted. Didn't read it correctly, or preventive actions were not sufficient, or sometimes there can be some sudden events that, of course, no machine learning ever can predict, because these events show no prior symptoms, no indications. And we could also now quantify the effect, on this that we can do for onshore wells and offshore wells. And you can see here the numbers. I mean, it's very significant. I mean, this is a quantifiable effect on your operations. by using this technology, right? And of course, the cost of software is invisible, and pretty much pays by itself after the first half of the world. So basically, what we see is that the StackPipe agents, they deliver value in all case studies, real time or post-drill. There is an analogy that I really, really like to use. This is our last slide, I think. This is an analogy that I really like to use, and it's about the machine learning and the car safety system, because we want to think of the car safety systems as something that is given, right? I don't know. Let's keep looking. So it's something that is given, and when you get into your car, you turn it on, you start driving. You don't even think about what type of safety systems you have, right? So you actually have, and there are a lot of safety systems. You don't even know half of them. You don't know how they work, and you probably don't even care. But what you care about is that these systems are there, and they're going to help you if needed. So you're going to see some warnings and alarms if something goes wrong. So exactly the same mentality is what we're trying to develop here, and what we want to achieve is that we want to have all these machine learning agents that cover all these different type of issues that can happen during the operations, so that you feel safe, that if something goes wrong, you will know about it ahead of time. I am convinced that this technology will eventually be used a lot on all the drilling rigs. Why? Because it's like insurance, right? It's like safety insurance. So if you can have it, why would you ever drill a well that wouldn't have this technology, right? That wouldn't tell you and wouldn't help you prevent any type of incidents that you may have. That's all we have, guys. So thank you so much. We're a little bit over time right now, but we're still going to answer all the questions you had. Also, here is the email. Please feel free to send any of your questions or inquiries or any other suggestions, recommendations, feedback to this email. We will be very happy to hear that. So let's go through the questions. Tim, I think you've been trying to answer it. Have you seen the questions?
Yeah. So I'll just read them out, and then I'll answer them at the same time. So first question we have from the audience is, are you just using surface data for your model, or do you have to input other aspects such as details about the BHAs, that's the bottom hole assemblies, well architecture, hole size, casing info, or mud characteristics? So we use standard surface drilling data. I mentioned earlier in the talk. We also use the mud density, but this can be either streamed or you don't need to have it present. We have kind of sensible defaults which will work with this, and then users are able to set it as well as they need to if this parameter is not being streamed. So for those who are not familiar with these operations, so offshore this is pretty much always available. In a lot of onshore operations, you don't always have the mud density. So this is why we have the ability for users to set it. And yeah, okay, so we've got a few more questions coming in, great. So second question, is the technology effective in the geothermal realm, specifically cases where air, foam, and mist fluid medium are used? So there are a couple of points to this, which I would have in this one as an answer. So if we think about three agents that we discussed earlier, we have differential sticking, mechanical sticking, and hole cleaning. So I think the one, differential sticking and mechanical sticking, work by looking at things like static friction and mechanical obstruction. So in those cases, I think they'll work fine in those kinds of fluid media. The hole cleaning, which is looking at things like the downhole ECD and estimating that in real time, that one would probably need to be tweaked a little bit to suit the geothermal realm. But I think the underlying methodology would remain sound. You just have to set it up such that it works with that kind of air or foam medium. or whatever type of fluid they're using in that case. All right, and lastly, sorry, not lastly, thirdly, what are some methods you use to ensure that your models extend to a variety of wells? So I mentioned earlier in the talk that we use curation very heavily. So we want very representative data sets. So what we do is we have a global data set which has stuff from all around the world. So we don't limit ourselves to any particular country or something like that. We're fortunate enough at this point to have data from every continent where people drill for oil and gas. So that's one thing. Another thing is that we talked about earlier that we use things which are approaches which are targeted at physics and physical indicators. So this really helps with generalization as well, because these sorts of physical indicators are replicated across wells. They're not idiosyncratic in the way that other pieces of information might be relative to a specific well. If you have difficulty moving something, and this might have a complex pattern in terms of how it manifests in terms of the time series data, but these patterns are more consistent than a lot of the sort of noise and variations that you might see between wells based on their equipment or formation specifics that you get in those cases. So through those two ways of looking at things, by curating data, by having things which look at physics rather than just trying to perform pattern recognition, that's how we can ensure that things work on a variety of wells. And through the blind testing, we can actually prove that as well. So in all the blind tests we showed before, these were done when the software had never been exposed to those fields or those basins. So we had something about Haynesville earlier. Haynesville was never in any of the data sets at the point when that test was done. So the methodology is quite generalizable from the testing that we've done. All right, next question is this compatible with all rig types, rig systems? So yeah, simple answer is yes. We don't explicitly use this information, and like I say, through the testing processes that we've used for previously unseen operations, we've had very good results. So yes to that question. All right, so someone here has asked, the ML agent can only forecast the problems that evolves over time and not happens at once, right? Well, yes and no. So it depends what time scale that is.
There are some questions I already answered here, but yeah, I mean, there are some sudden events that can happen that show no prior symptoms and no prior indications that are impossible to predict, but those are rare. We see that over 90% and even 95% of drilling incidents show some type of early indications that can be picked up.
Yeah. So in terms of stuff that's very sudden, so if you have things like wellbore collapses, they're quite rare, but when it happens, you can get sort of catastrophically stuck very, very quickly. If it's something which is happening on a quick in terms of oil operations time scale, which might be like 40 minutes, 30 minutes, those things do get detected, and typically quicker than a human would be able to. And then also, like the question suggests, stuff that happens evolving slowly over time. Software is very good at that as well, because monitoring specialists tend to look at the last hour or two, whereas if you've had these kinds of indications building up from before that as well, the software is keeping hold of that and then reporting on it as you go through.
Yep.
And the final question we have here is the only required data source is the EDR through WITSML. So yeah, that's correct. We typically use WITSML, but like I say, it's very standard surface parameters from the EDR for feeding to the software. All right, I think that's all of the questions I can see, at least in the interface here. So
what is the minimum data frequency required? 1 second data is perfect. 5 seconds data is great. 10 seconds is something we can manage, but there can be some uncertainties. That's all the questions I see.
All right.
No. All right. Well, thank you so much, everyone, for participating and for being here with us today. Again, this is our email. Please send your additional questions or anything you want. We'll be happy to answer. Thank you again, and we hope to see you again on our next webinar that we'll announce at some time. Hope this
Thank
you
you,
like
everyone.
that was very useful for you. Thank you, team.
Have a great weekend.
Have
Bye,
a great
guys.
to everyone.